Traditional software engineering relies on building reliable systems through human-coded logic, discrete algorithms, and third-party services linked via REST APIs. It is tempting to assume that integrating an LLM or machine learning model is just another API call. However, the invisible pressure of non-deterministic workloads causes traditional engineering pipelines to splinter when they are treated as standard library integrations. Standard pipelines bottleneck and fail under heavy AI loads because they are optimized for predictable, scalar execution. Traditional performance metrics like network latency become secondary to the massive memory exhaustion and thread pool saturation inherent in processing high-dimensional tensor data. Successful AI integration demands an entirely distinct compute ecosystem, one governed by rules that contradict the assumptions of traditional software development. To build reliable AI systems, engineers have to move past the mental model of exact execution and rebuild their understanding of the stack from the hardware up. We map the difference between environments. Traditional software is deterministic. AI is probabilistic. Deterministic outcomes are exact, explicitly hard-coded by an engineer. Machine learning outcomes are fluid, continuous approximations determined by tensor flows, resulting in a distribution of probabilities rather than fixed values. The core engineering task has shifted. It is no longer about writing exact execution rules, but designing systems capable of calculating accurate approximations. Traditional engineering solves complex problems using discrete searches, such as A-star pathfinding or constraint satisfaction problems, to navigate a defined grid of possibilities. Machine learning replaces this discrete grid with a continuous landscape of mathematical loss. An algorithm navigates this using gradient descent. It calculates the error's slope, taking steps toward the lowest valley, adjusting internal weights to minimize loss. This optimization happens through different learning styles. Parametric learning optimizes a fixed set of weights, while non-parametric learning allows the model structure to grow as it encounters more data. In this model, the engineer does not write the rules of the search. Instead, the engineer writes the optimization parameters that allow the machine to approximate those rules. Modern problem-solving is an act of mathematical optimization over continuous variables, making strict heuristics insufficient for modern AI workloads. Traditional software success is measured by time and space complexity, typically expressed through Big O notation. Evaluating a neural network based solely on its runtime or memory footprint misses the primary objective of the model. Speed does not equate to accuracy or utility. The primary metric for machine learning is generalization. This is tracked by comparing training loss against validation loss. Generalization measures the ability of an algorithm to accurately predict or generate outputs when exposed to entirely unseen, real-world data. When an algorithm memorizes training data perfectly, but fails in production, it has entered a state of overfitting. This represents a systemic failure, regardless of how fast the code executes. A highly optimized lightning-fast model is an engineering failure if it lacks the capacity to generalize its approximations to unseen environments. Traditional data retrieval relies on exact ID matching within relational databases, which is effective for structured, predictable queries. Generative AI and LLM agents require a different approach because they function on conceptual similarity rather than exact match logic. This requires transforming rigid relational rows into high-dimensional embeddings, arrays of numbers representing meaning. Vector databases execute queries by calculating mathematical distances, like cosine similarity, finding data points nearest to the query in this multidimensional space. To make these searches viable at scale, systems use HNSW, or Hierarchical Navigable Small World Graphs. They allow for approximate nearest neighbor searches, significantly faster than checking every individual vector. Supporting these vector systems requires specialized data warehousing pipelines that utilize OALAP, star schemas, and cube pre-computations to handle the pre-processing of raw data. In the AI era, data retrieval is a geometric distance calculation, moving away from the primary key lookup entirely. Probabilistic math demands a specialized physical compute structure. Software and hardware must be co-designed to handle these workloads efficiently. We can see this in the difference between a standard CPU and specialized AI hardware like GPUs. A traditional CPU, designed for sequential instructions, immediately bottlenecks when attempting to process the massive vector-valued returns of a neural network. GPUs use SIMD, single instruction, multiple data. This parallel execution allows the hardware to process massive matrices of weights simultaneously, the only efficient way to run deep learning models. Despite the power of GPUs, massive foundational models often carry too much compute overhead for edge devices or standard enterprise servers. Engineers address this through post-training optimizations, like pruning and quantization. These techniques shrink the model's footprint by removing redundant connections or reducing mathematical precision without destroying the model's accuracy. In machine learning engineering, software and physical silicon are deeply coupled. Ignoring parallel architecture leads to systemic failure. Transitioning to this ecosystem involves a critical trade-off. By moving away from deterministic logic, developers lose direct transparency into how a system reaches its decisions. Rigid mechanical control is entirely replaced by fluid, opaque processes that are difficult for humans to audit directly. Enterprise software requires accountability, which makes explainability a mandatory component of machine learning engineering. Mathematical tools like shop values pry open this black box, quantifying exactly how much each input feature contributed to a specific output. These techniques map probabilistic outputs back into human-readable insights, showing which factors most heavily influence the model's final decision. ML engineering concludes with the mathematical proof of the decision-making process, providing the evidence required to trust non-deterministic systems. This concludes the reconstruction of the engineering mental map for the AI era. The modern pipeline is an interconnected flow, from data warehousing to vector embeddings, through neural architectures, and finally to parallel hardware execution. The entire stack is built to navigate and process non-deterministic, vector-valued variables efficiently. While mastery of discrete algorithms and API integration was the standard for years, relying on them exclusively in this new environment is a liability. Success in this space requires embracing continuous mathematics, prioritizing probabilistic generalization, and optimizing for specialized hardware. This mental map provides the technical grounding required to deploy and scale agentic systems effectively within complex AI environments.